In the last week lecture session, we had ended the chapter 5 with some operation related to the BJT. For today's lecture session, we will discuss about new chapter which operational amplifier. Okay. Similar within the previous lecture session, there will be parts of this lecture video where the students require to answer questions based for the lecture session's attendance. Okay, right, let us begin the lecture. As usual, I will start my slide by listing down sub-chapters of the chapter 6. For this lecture session, there will be fixed sub-chapters to be covered. We will start our lecture with introduction of the operational amplifier, or we call it in short as op-amp. We will discuss about the basic operation of op-amp. Later we will go in the sub-chapter of inverting and the non-inverting amplifier. Lastly for today is the summing amplifier. Okay, let us start our lecture. An operational amplifier or op-amp is an active circuit element designed to perform mathematical operations of addition, subtraction, multiplication, division, differentiation, and integration. Normally the op-amp is used in the application which related to provide voltage amplitude changes such as amplitude and polarity, oscillators, filter circuit, and instrumentation circuit. The op-amp is linear integrated circuit and widely used in analog electronic system. This op-amp is built with the internal construction includes a number of transistors, diodes, resistors, and capacitors in a single tiny chip of semiconductor material. It is packaged in a single case to form a functional circuit. As an example of the op-amp here, we will use the 741 op-amp. It has 8-pin package where it is packaged in a single case to form a functional circuit. The other 5 are, pin number 2 is inverting input, while pin 3 is for non-inverting input. The output is at the pin 6. For the power supply purposes pin 7 and 4 for each positive and negative of the power supply. We can have the idea of this 741 in an illustration images as in the figure on the right hand side of this slide. This is what we have internally inside the 741 op-amp. Each of the pin that we discussed in the previous slide consists of a combination of several transistors to allow a dedicated function such as amplifier. To portray the op-amp with symbol, the standard symbol for the op-amp is a triangle and it has 2 inputs and 1 output. The inputs are marked with minus and plus symbol to specify inverting and non-inverting inputs, respectively. Here minus is for inverting input, and the plus is non-inverting input. An input applied to the non-inverting pin will appear with the same polarity at the output. An input applied to the inverting pin will appear inverted at the output. Inverting and non-inverting refers to the behavior of the output signal after been applied with an input signal, which means inverting is for the case when a positive signal will be inverted as the negative side or the opposite of the signal. To introduce the op-amp's input mode operation, we will show a figure which will help student to understand the basic idea of the output and the both inverting and non-inverting input. In this slide, we have two example cases of single-ended input type of op-amp. The single-ended input is when the inputs are marked with minus and plus to specify inverting and non-inverting inputs, respectively. An input applied to the non-inverting pin will appear with the same polarity at the output. An input applied to the inverting pin will appear inverted at the output. On the left is when signal is applied to positive input or to non-inverting input. As from the name itself, non-inverting implies the output as the same as the input given which any change polarity. On the other hand, when the input is applied to the negative input or to the inverting input, the output will be opposite from the given input signal. The second type of input mode operation of op-amp is double-ended input. For this type, the input signal is applied to each input similarly. On the left, both inputs are applied with VD but neither input is at ground. Here the amplified output is in phase with input applied between AND VE and VE inputs. While on the right-hand side, the input signal is applied separately. On the output side, the signal is produced as the difference of the two input signals given as VI1 and VI2. For the third type, common mode operation, same input signals are applied to both inputs of op-amp with the 0 volt as ground because the two signals equally amplified but with opposite polarity signals. For the basic operation of the op-amp, it is divided into two, non-ideal and ideal operation. However, the ideal operation will be used throughout the analysis. Even the non-ideal op-amp is seldom used in the analysis. As to understand the concept, we will take a look the general idea of it. It has several characteristics to be followed as the high open loop gain, high input resistance and low output resistance. Here, we understand that the VD on the input side is the voltage difference of V2 and V1. Where V1 is the voltage between the inverting terminal and ground and V2 is the voltage between the non-inverting terminal and ground. Now we will move to the ideal operation type of op-amp. The characteristic of this type will be having infinite open loop gain, infinite resistance, and zero output resistance. It is different from the previous one which has been discussed before. The ideal op-amp model is showed as in this figure. For the ideal op-amp some consideration needs to be followed. We can see that the both current I1 and I2 in the input pins are 0. Then, the voltage across the input terminal are also 0. VD is V2 minus V1 is 0. From here, as this difference is 0, later we know that the V1 finally is equal to V2. For this reason, I hope that these two ideas of current and voltage consideration will be understood by all of you. These two will mostly use later in example throughout the slide. Now, we will take a look at an example which related to the ideal operation. We need to calculate the closed-loop gain VO by Vs and find the output current as I0 when the Vs is 1 volt. OK. In the ideal op-amp, we need to remember two things: the current and the voltage. Both input I1 and I2 is 0. And the both V1 and V2 is equal. Here, since the I1 is 0, the 40 kΩ and 5 kΩ resistors are in series position, the same current is flow through them. And here, also notice that V2 is Vs since we know that the idea of V1 is V2. V1 is analyzed by considering the voltage division principle. 5,000 ohms by 45,000 ohms to the VO will be VO by 9. Then, as we know that V1 equals V2, the closed-loop gain is Vs equal to VO by 9. Also, if we consider the ratio between the two voltages will be equal to 9. At the O point, the current I0 from KVL will be the additional of 2, which VO by the both 5,000 and 40,000 ohms and VO by 20,000 ohms. Now, when we apply the Vs equal to 1 volt, VO will be 9 volts, which was considered from the voltage ratio above. Later, as substituting the VO equal 9V, the output current I0 will be 0.65 mA. Inverting amplifier. The figure here presents the inverting amplifier. From this figure, we understand that the non-inverting input is grounded, while V1 is connected to the inverting input which going through the R1. Another feedback resistor as RF also is connected here between the inverting input and output. Our goal is to obtain the relationship between the input voltage 6 and the output voltage VO. When we apply the KCL at node 1, I1, and I2 is similar. It is later will direct us to the two voltage and resistance relation here. But for an ideal op-amp, V1 equals V2 equals 0, since the non-inverting pin is grounded. Hence, from the middle equations, we can simplify them into blue shaded area equation below for finding the relation VO and VI. Now we will have VO is equal to 6 by the negative ratio of RF and R1. For the voltage gain, AV will be equal to VO by VI. Then, we can rearrange the equation in the previous slide to be as AV will be equal to minus RF/R1. The designation of the circuit as an inverter arises from the negative sign. Here is the example of the inverting amplifier. Say that the input voltage is 0.5 volts. Calculate the output voltage and current in the 10,000 ohms of resistor. To do this, remember the voltage gain equal to minus RF and R1. We can utilize this equation to one of the voltages. Then the output voltage later will be minus 1.25 volts as the given input is 0.5 volts. The second is current through the 10,000 ohms resistor. Here, by referring the Ohm's law, I will be 50 microamperes. Okay, now, we will discuss about the non-inverting amplifier. As the name shows, the non-inverting input is when the voltage applied to the positive input pin, and the resistor R1 is connected between the ground and the inverting pin. As the I1 and I2 is equal, we can have the voltage and resistance ratio equation here by minus V1 and R1 and the VI minus VO and RF. As we understand, the V1 equals V2 is also equal to VI for this case. The equation above can be changed as the relation between voltage output and voltage input. For the voltage gain here, AV is 1 plus with the RF by R1. The output has the same polarity as the input, thus it is named as non-inverting amplifier. For the non-inverting amplifier, we will have a voltage follower or unity gain amplifier. It is called the follower as the output is following the input. This will happen when the RF is 0 and R1 is infinite or open circuit. To have an idea about the non-inverting amplifier, we will have this example. We need to calculate the output voltage VO. Applying the KCL at the node A, the voltage different for this current are represented by this equation, the middle of this slide. Later, as VA equals VB and equal to 4 volts, the output voltage will be calculated, and it is 1 volt. There is another type of amplifier that combines several inputs and produces an output that is the weighted sum of the inputs. Figure below shows the connection of summing amplifier, also called a summer. We can see from the figure on the left-hand side, it is an inverting amplifier with multiple inputs. Note that it can have more than 3 inputs. When we apply the KCL at node A, the current I is equal to the additional of current 1, 2, and 3. Listing the voltage difference at each current with its resistor, we will have the equations in the middle side of this slide. Later, after applying the VA as 0, we will have all the current as the 4 equations below. Arranging these 4 equations together will direct us to have the equation VO with other voltage 1, 2, and 3. Looking into this long equation, we can easily reflect to the equation that we met in the inverting amplifier. As to see the real idea of this summing amplifier works, we have an example here. We need to calculate the output voltage and current based on the following the op-amp below. As we are given 2 inputs for the summing amplifier, the output voltage can be calculated as in the equation below. Finally, we will have the VO as minus 8 volts. The current I0 is the sum of the currents through the 10,000 ohms and 20,000 ohms resistors. Both of these resistors have voltage VO equals 8 volt across them, since VA equals VB equals 0. Hence, the output current can be calculated by using the Ohm's law at the 10,000 ohms and the 2000 ohms resistors. The output current now is minus 4.8 milliampere. With that, I end my lecture for this chapter 6 part 1. I hope that you all gained knowledge and ideas this chapter.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.